Picture this scenario, right? It's late July, and you step outside just to grab the mail.
Oh, brave.
Yeah, right. And it feels like you've just walked into a preheated oven because it is like 105 degrees out.
Absolutely brutal.
Totally. So you go back inside your house, you're pacing around, and you're glaring at the thermostat. Your air conditioner has been roaring, just running flat out since noon.
Naturally.
But that little digital number on the wall is stubbornly stuck at 78 degrees.
Yeah.
So you wipe the sweat off your forehead and you ask yourself the exact question everyone asks in this exact moment, which is my AC broken?
It's the ultimate summer panic, honestly. And the instinct is always to assume, a mechanical failure.
Right, because we expect it to just work.
Exactly. We've been conditioned to view our climate control as this absolute thing. You set a number on a dial, and you expect the machinery to just, conquer nature to deliver that number.
Regardless of the fact that the asphalt in your driveway is literally melting.
Yeah, exactly.
We tend to expect this straightforward cause and effect relationship. But for today's deep dive, we're pulling from a fascinating stack of highly technical engineering sources to figure out the physics of what is actually happening.
And it's really not what you'd think.
Not at all. We're digging into the Air Conditioning Contractors of America, the ACCA, and their Manual J design conditions.
Very important document.
Plus, we've got extended performance tables from major HVAC manufacturers, compressor operating envelopes, and decades of field data from brutal summer heat waves.
Yeah, the data tells a completely different story than the one we imagine when we're sitting there sweating in our living rooms. The reality is, it's far more mathematical.
Right. So our mission today is to explain exactly what 105 degrees outside does to that metal box humming outside your window.
For sure.
We're going to separate a system that is merely surviving from one that is genuinely failing and give you actionable tools to help your equipment through, the worst 2 weeks of the year.
That's the goal.
Okay, let's unpack this. The fundamental concept here seems to be this contract our air conditioners have with the weather.
Yeah.
Because it seems like we fundamentally misunderstand the parameters of the deal we signed when these systems were installed.
The contract analogy is honestly the perfect way to look at it. And it revolves around something called the ACCA Manual J design condition.
Manual J, right?
Right. When a home is built or, when a reputable contractor installs a new system, they don't just guess what size unit you need based on the square footage.
Like they don't just say, 2,000 square feet, give them a big one.
Exactly. They don't do that. They use a really complex formula to calculate the heat load of the house.
Okay.
They account for the orientation of your windows, the R value of your wall insulation, even the heat generated by the appliances inside. And this is the key, they had to calculate that load against a specific historical target.
So a baseline of what hot historically means for that specific geographic region?
Precisely that. So in central Oklahoma, for example, the historical mathematical baseline, the Manual J design temperature, is 97 degrees.
Wait, really? Just 97?
Just 97. The engineers sized the equipment to hold an indoor temperature of 75 degrees when it is exactly 97 degrees outside. That is the contract.
Wow.
So when the weather hits 97, the system is operating perfectly within its design capability.
But when the thermometer spikes to 105 degrees, the machine is pushed way past its design parameters.
Exactly. We are no longer operating under the contract. The system isn't breaking. It's just, it's attempting to balance an impossible equation.
And from the extended performance tables in our sources, that math gets incredibly brutal due to this phenomenon where rising demand meets falling supply.
What's fascinating here is the physics of that. As the outdoor temperature climbs from 97 to 105, the heat load on the physical structure of your house just skyrockets.
Because of the sun.
Yeah, the sun bakes the roof, the siding absorbs thermal energy, the windows radiate heat inward, your demand for cooling spikes. But at the exact same time, the air conditioner's actual capacity to cool the house mathematically drops.
This comes down to the temperature differential, right? What engineers call the delta T.
Yes, exactly.
Because an air conditioner doesn't actually make cold air. It absorbs heat from inside your house and uses refrigerant to transfer that heat outside.
Right, it's a heat mover.
But heat only flows naturally from a hotter object to a colder object. So the closer the outdoor air temperature gets to the temperature of the hot refrigerant, the harder it is to transfer that thermal energy.
That is the core mechanism at play. To visualize this, let's look at a nominal 3-ton condenser.
Okay.
And just a quick note, in HVAC terms, a ton of cooling doesn't refer to weight.
Right.
It represents the amount of heat energy required to melt 1 ton of solid ice over a 24-hour period, which is 12,000 BTUs per hour.
Okay, so a 3-ton unit removes 36,000 BTUs of heat per hour.
Precisely. At 95 degrees outside, that unit delivers its full 36,000 BTUs. But by the time the ambient temperature hits 105 degrees, that exact same machine loses 8 to 10% of its cooling capacity.
Just because it's hotter outside.
Simply because it cannot dump the heat into the already boiling atmosphere.
Oh, wow. It sounds like driving a car up a steep mountain with a full trunk. I mean, the engine isn't broken just because you have the pedal to the floor and you can't hit 70 miles per hour, right?
That's a great way to put it.
It's just dealing with extreme physics.
Yeah.
So if your indoor temperature creeps up 2 or 3 degrees in the late afternoon and then successfully recovers at night when the sun sets, you're witnessing arithmetic playing out in real time, not a mechanical failure.
Which is a profound shift in perspective.
Okay.
You're watching a machine operate at its absolute maximum physical limit and survive.
Okay, but if the current system can't handle the mountain, why don't people just buy a bigger engine? I mean, the immediate temptation for anyone sitting in a 78-degree living room is to simply buy a bigger AC unit.
Right, the intuitive leap is, hey, let's install a 4-ton or a 5-ton unit so the house is always covered.
Exactly.
But in the world of HVAC, we know that oversizing a unit leads directly to the trap of short cycling.
Short cycle?
Yeah, oversizing is arguably the worst mistake a homeowner can make.
Wait, really? The worst mistake.
Oh, for sure. A massive air conditioner would indeed blast the house with cold air and hit 72 degrees on a 105-degree day. But an AC sized perfectly for that one extreme afternoon is drastically oversized for the other 99% of the year.
Ah, I see.
On a normal 85-degree day, that massive unit turns on, drops the temperature rapidly over like 5 minutes, and then shuts right back off.
And the problem there is the difference between sensible cooling, which is lowering the actual temperature, and latent cooling, which is removing humidity.
Exactly.
If the system only runs for 5 minutes, it lowers the sensible temperature, but it completely fails to perform the latent cooling.
Right. The mechanism of dehumidification requires time. The indoor evaporator coil has to get cold and stay cold for a sustained period to wring the moisture out of the air. It functions exactly like condensation forming on the outside of a glass of ice water.
Oh, that makes total sense.
So a short-cycling, oversized unit leaves all that water vapor behind. You end up with a house that reads 72 degrees on the wall, but feels like a damp, clammy cave.
Yuck.
Plus, starting and stopping a heavy compressor motor every 10 minutes drastically shortens the lifespan of the equipment and, honestly, spikes your electric bill.
Okay, so upsizing the machinery is totally off the table.
I don't.
Here's where it gets really interesting, though. You're saying the system is often taking the blame for what the ductwork wasted. If the 3-ton unit is correctly sized to handle the house, but we're still losing cooling power, the issue is often happening in transit. Like, the machine is producing cold air, but the house is betraying it, specifically up in the attic.
The attic is a notoriously hostile environment. On a 105-degree afternoon, an unconditioned attic space under a dark roof can easily reach 130 to 150 degrees.
That is insane.
It acts as a massive thermal oven. Now, consider that most residential ductwork is suspended right in the middle of that oven.
Oh, wow. So the air conditioning system works incredibly hard to produce a crisp 55-degree supply of air leaving the indoor coil.
Right.
But that chilled air then has to travel through thin sheet metal or like flexible ductwork surrounded by a 140-degree environment.
It acts as a giant heat exchanger in reverse.
Oh, no.
Yeah. The standard insulation on flexible ductwork, usually an R6 or R8 value only, delays heat transfer. It doesn't stop it.
Okay.
So by the time that 55-degree air travels 40 feet to the furthest register in your primary bedroom, it might have absorbed 10 degrees of heat.
So if the air at my furthest register is barely cool at 4 p.m., I shouldn't be yelling at the metal box outside. I should be looking at my attic insulation.
Exactly. The metal box outside is likely doing its job perfectly. The loss is happening in the ductwork.
That reframes the entire problem. The machine is basically fighting a war on two fronts, the ambient heat outside and the hostile architecture of the house itself.
It really is.
Understanding that macro physics level is crucial. But the sources also detailed the micro-level damage. We need to look at what that 105-degree heat is actively doing to the specific components under the hood of the condenser unit sitting in the backyard.
Yeah, the toll on the compressor is just staggering.
Because it's the heart of the cycle, right?
Exactly. Its job is to take the warm, low-pressure refrigerant gas returning from the house and squeeze it tightly, raising its pressure.
Right.
And according to the laws of thermodynamics, when you compress a gas, you also raise its temperature.
Okay, so to successfully dump the heat from your house into a 105-degree outside environment, the compressor has to squeeze that refrigerant until it reaches a temperature significantly hotter than 105 degrees.
Usually around 120 or 130 degrees.
Wow. Squeezing that gas is like aggressively pumping a bicycle tire. I mean, the friction and pressure generate intense heat, so the hotter it is outside, the harder the compressor has to squeeze to achieve that temperature differential.
Yeah, and in engineering terms, this causes the head pressure within the system to spike. Pushing against that immense head pressure requires the compressor's electrical motor to work significantly harder. When an electric motor works harder, its electrical amp draw goes up.
And that creates more heat, right?
Right. Higher amp draw generates secondary electrical heat inside the motor windings, and heat is the ultimate enemy of internal motor insulation.
Oh, man.
Every extra degree of discharge temperature literally eats away at the lifespan of the copper winding insulation inside that steel shell.
And if your outdoor coil is, like, clogged with dirt or grass clippings, restricting airflow?
The pressure climbs even higher, the motor can't cool itself, and it eventually just burns out.
It's a brutal cascade of pressure and heat, and the compressor isn't the only component fighting for its life, is it?
Not at all.
The capacitors are also sitting in that electrical box attached to the condenser. They're baking in full sun, usually mounted over a concrete slab that absorbs and radiates solar heat all day long.
Capacitors are highly vulnerable to this environment. The best way to visualize a run capacitor is not as a battery, but rather as a heavy-duty water tower or a tightly coiled spring.
Okay, a spring.
Yeah. An air conditioning compressor is a heavy piece of mechanical equipment that requires a massive, instantaneous jolt of electrical torque to overcome inertia and start spinning.
So a capacitor stores electrical energy and dumps it all at once to provide that kick.
Precisely.
The brutal math detailed in our sources regarding these capacitors is shocking. Based on the Arrhenius equation for electronic components, for every 10 degrees Celsius of extra heat a capacitor is exposed to, its expected lifespan drops by half.
Drops by half. The deterioration is exponential.
That's crazy.
If a tech tested your capacitor during a spring maintenance check and noted it was slightly out of tolerance or marginal, the sustained heat of late July is going to push it to failure.
Because of the heat.
Yeah, the dielectric fluid inside literally boils and expands, popping the top of the capacitor outward until the internal connections just break.
So what does this all mean? It means deep summer is basically execution season for parts that were already struggling.
Very well said. Heat reveals every mechanical weakness.
Which brings us to the triage phase for you, the listener. We know the physics are unforgiving and the components are under immense strain. How do you tell the difference between a system that is just sweating out the heat and one where a capacitor has actually been executed?
The baseline for normal during a heat wave might actually surprise people.
Okay, let's hear it.
First, if the unit runs continuously without cycling off from early afternoon until well after sunset, that is normal behavior.
Running nonstop is normal.
Completely normal.
Okay.
Second, an indoor temperature drift of 2 to 3 degrees over the afternoon peak that fully recovers by nightfall is also completely normal.
Right, the mountain analogy.
Exactly. Third, if you place your hand over the exhaust fan on the top of the outside unit and the air blowing upward feels like a hot hairdryer, that indicates the system is actively and successfully ejecting the thermal energy from your house into the atmosphere.
Along with a significantly higher electric bill at the end of the month, I bet.
Yeah. Which is the inevitable cost of that continuous amp draw.
So if the system is running nonstop, it's slightly warm inside, and the fan is exhausting hot air, the system is surviving, there's no need to tie up emergency service dispatch lines.
Right. Let the technicians handle the genuine failures.
Because an actual failure presents very clear red flags. Right.
Yes. This raises an important question. What is abnormal? If the indoor temperature climbs 5 or more degrees and fails to recover overnight, the system has lost capacity.
Okay.
If you check the indoor room registers and the air blowing out is ambient room temperature rather than noticeable cold, the heat exchange process has completely stopped.
And what about that capacitor spring?
The classic sign of a dead capacitor is when you walk outside and hear the condenser unit humming aggressively, but the fan blade is entirely stationary.
Ah, so the motor is trying to start, which causes the hum, but it lacks that jolt of energy.
Exactly. Another critical red flag is repeated electrical breaker trips. If you reset the breaker at your main panel and it immediately trips again, Do not continue resetting it.
That sounds dangerous.
It is. A tripping breaker is a safety mechanism indicating a dangerous electrical short or a completely locked up compressor motor. Forcing power into it can literally cause a fire.
Yikes.
You also want to watch for water pooling around your indoor unit. Because the system is running continuously, it's wringing maximum humidity out of the air.
Right.
If the primary condensate drain line gets clogged with algae, the emergency float switches will just shut the entire system down to prevent flooding your ceiling.
Okay, but wait, there is one paradox in our sources that stands out. Seeing ice on the refrigerant lines or covering the indoor coil in the middle of July, that feels like a paradox. Why would extreme heat cause ice?
It's a really fascinating mechanical failure. Ice formation almost always points to a severe lack of airflow across the indoor evaporator coil.
How does that happen?
The indoor coil drops to a very low temperature, relying on the warm return air from your house blowing across it to provide a heat load. The warm air gives its heat to the coil, which cools the air.
Right.
But if the air filter is completely choked with pet hair and dust, that warm air never reaches the coil.
Oh.
Without that steady supply of heat from the house, the temperature of the refrigerant drops below freezing. The ambient humidity in the air condenses on the freezing metal and turns to frost,
And then the frost acts as an insulator, dropping the temperature even further.
which creates more frost. It's a cascade effect until the entire coil is encased in a solid block of ice. The system literally suffocates and freezes itself.
Wow. So the crucial takeaway from the field data is how to handle a frozen system. If you see ice, you must turn the system completely off at the thermostat and leave the indoor fan running to thaw it out.
Yes. A technician cannot accurately check refrigerant pressures or airflow across a solid block of ice.
Right. Calling for immediate service while the unit is frozen just means you're paying an hourly rate for a technician to stand there and watch ice melt.
Exactly. Taking control of the situation before failure occurs is where you, the homeowner, actually have some power.
So what can we physically do to help our system survive the heat wave?
The sources outline several actionable steps. The first rule is thermostat management.
Okay.
Leave the thermostat on a hold setting rather than trying to chase the temperature down in the heat of the day.
Because dropping the setting from 78 to 70 at 3 p.m. doesn't magically make the air coming out of the vents any colder, right?
Exactly. It merely demands that the machine run infinitely, chasing an impossible target.
Okay, well.
Managing the physical environment of the machinery is equally important. Ensure a 3-foot clearance around the outside condenser, cut back shrubs, move patio furniture, eliminate anything restricting airflow.
Because the system needs to move massive volumes of air to reject heat.
It's exactly. Indoors, close west-facing blinds afternoon to block direct solar radiation and run ceiling fans in occupied rooms.
Right, because the evaporative cooling effect of moving air across human skin makes a room feel several degrees cooler, which allows you to tolerate a slightly higher thermostat setting.
Spot on.
I actually noticed this recently with my own unit. I went outside, and the condenser was coated in a thick layer of cottonwood fluff and grass clippings. It looked like the machine was wearing a winter sweater.
Oh yeah, that is the worst.
That debris acts as an insulator, preventing the heat transfer from the aluminum fins to the outside air, which destroys that critical delta T efficiency we talked about.
Yep. Disconnecting the power at the outdoor breaker box and using a garden hose on a gentle setting to rinse the fins from the top down is one of the most effective things you can do.
Just a gentle rinse.
Yeah. Washing off that insulating layer restores the surface area for heat exchange, which directly lowers the head pressure on the compressor, reducing the amp draw and the internal heat.
The sources also detail a strategy called load shifting or pre-cooling, which utilizes the concept of thermal mass. What is that?
Utility companies actually frequently utilize this strategy with large commercial buildings to protect the power grid, and it applies perfectly to residential homes.
Okay.
The regional power grid hits maximum strain during the deep summer afternoons, typically between 4 p.m. and 7 p.m.
Right, when everyone is home.
Exactly. Instead of demanding peak performance from your air conditioner during those hours, you shift the load to the morning.
Oh, I get it. During the late morning, when the ambient temperature is only 85 degrees, the air conditioner has plenty of excess capacity and operates highly efficiently.
Exactly. By dropping the thermostat to 70 or 71 degrees then, you aren't just cooling the air, you are chilling the thermal mass of the house.
So the heavy furniture, the hardwood floors, and the interior drywall all absorb that cooling.
They act as a massive thermal battery. Right before the afternoon peak hits around 3 p.m., You bump the thermostat up to a higher holding temperature, like
Right.
76 or 78.
Oh, so it's like getting a running start before a massive hill climb.
That's a perfect way to put it. When the 105-degree heat hits the exterior, the chilled thermal mass of the house slowly absorbs the incoming heat.
So you're doing the heavy lifting when the machine is most efficient, which is kinder to that compressor we talked about.
Yes, the air conditioner coasts through the most brutal part of the day without being forced to run continuously at maximum head pressure. It is incredibly protective of the compressor life and lowers peak energy demand.
So the core realization for you, the listener, is this. At 105 degrees, your air conditioner isn't failing, it is surviving.
Absolutely.
It is working past its design contract against rising heat loads, dropping capacity, and the brutal thermal dynamics of your attic. As long as it's not encased in ice, leaking water, tripping electrical breakers, or refusing to start, keep the filter clean, wash off the cottonwood fluff, and just let it run.
Understand the physics and cut the machine a little slack.
All right.
But, if we connect this to the bigger picture, a much deeper conversation emerges from these sources. We established earlier that the ACCA Manual J design parameters are built on historical weather averages, right?
Oh, the 97-degree baseline for central Oklahoma.
But the climate baseline is shifting. As extreme heat waves become longer, hotter, and more frequent globally, those historical averages, they no longer reflect reality.
So the math is changing.
Exactly. If 105 or 110 degrees becomes the sustained normal for weeks at a time, the foundational mathematics of how we design our homes and machines will have to fundamentally evolve.
Wow.
It raises a fascinating question based on the engineering data. Will the deeply inefficient, oversized air conditioner we warned against today become the absolute baseline necessity of tomorrow?
That is a staggering thought. And how will our aging electrical grids handle the exponential surge in amp draw when every single home is forced to upgrade just to honor that new design contract?
It's an engineering challenge we're going to have to face.
Well, that gives us all something to think about. So next time you're staring at a thermostat stuck at 78 degrees in late July, remember the massive physics equation playing out in your backyard. Your AC isn't broken, it's fighting gravity. Give it a gentle rinse, utilize your ceiling fans, and ride out the heat wave.